In this video, we discuss problems 93 through 96, which are additional problems on compound interest. The problem statement says, complete the table by determining the amount of money P, that's called the present value, that should be invested at a given interest rate to produce a balance of $100,000 in T years when we're compounding interest N times per year. So basically the idea is this. We looked at that formula for the amount, the account balance, if we had a particular principal. So we said, okay, if we we invest this amount right now, what will the account balance be, T years from now? But you can just take that equation and you can solve it for P in terms of A, and that will allow you to determine how much you should invest now to get that amount, that account balance that you're seeking later. So in this case, we are seeking a balance of 100,000. So A is equal to $100,000, and we're asked to find P. Now, there are two formulas that we use for this, either the compound interest formula, or excuse me, the continuously compounded interest formula, or the other one, where we're compounding interest A times per year. So let's look at that. Actually, it looks like some things have changed on this. The account balance is equal to P times 1 plus that interest rate divided by the number of times you're compounding that interest per year, raised to the number of times the interest is compounded. So it's going to be that N times per year times the number of years. If I take this equation and I solve for P, or I can solve for P by taking both sides of the equation and dividing by this 1 plus R over N raised to the NT. But dividing by an exponential is the same as multiplying by the same exponential with the opposite exponent. So I can multiply both sides by 1 plus R divided by N raised to the negative NT, and that will give me my value for P. What I've done is I've solved for P by dividing both sides by this, and dividing by an exponential is the same as multiplying by that same exponential, but with the opposite sign. So P is equal to this. And then we get this curve. But we're only interested in this curve for times greater than or equal to 0. Because we want to know how much we should invest right now at time t equals 0. So this is the curve that we're interested in, this purple curve right here. And then if we evaluate that function at t equals 0, we get that amount that we're seeking. Now, if we evaluate this function at time t equals 0, we get that desired balance of 100,000. All that's saying is that if you want $100,000 in your account right now, well, you have to deposit $100,000 in your account. Now, the idea is if you don't necessarily need to have $100,000 right now, but you'd like to have $100,000, 40 years from now, you don't have to invest nearly as much right now if you're willing to leave it alone for 40 years, essentially. So this curve that we have here is describing the amount that you should invest right now if you're willing to leave the money in the account for T years, and if you want to have $100,000 T years into the future. We've got that. And the question asks us to complete a table. So let's type in our table. So the table they have on your or in your textbook, they're just asking us for that present value, the amount that we should deposit right now for T years. So I'm going to, in order to create that table, we go to the plus sign in the top left-hand corner, then select table, it's the third one on the list, and it gives you this X1, Y1. Instead of calling it X1, Y1, I'm going to call that T1. And then the principal value. But that principal value can be given by that function. I had P sub N times per year. I want that evaluated at T1. For T equals 1 year, T equals 10 years, 20 years, 30 years, 40 years, and 50 years. And notice that this is auto-populating that P, that present value for T equals 1 year, 10 years, 20 years, 30 years, 40 years, or 50 years. For the amounts given here. This is where the desired amount in the account after T years is $100,000, and we're compounding 365 times per year with an interest rate of 5%. Now, the problems vary. Problems 93 through 96, excuse me, in that they change the interest rate and then they change the number of times you're compounding interest per year. So we can do that by adjusting the value of n with this slider, and then adjusting the value of r here. You can use the slider or you can just type in the value of r. Either way is fine. And this will give you the principal value, not principal value, the present value that you need to invest so that you have that $100,000 so many years later. Let's actually use pencil and paper. We'll do some calculations and then we'll compare it to the values in the table here. Now for 93, we're asked to find that amount of money that we should invest at interest rate R to produce a balance of $100,000 in T years, given that our interest rate is 5% and that we're compounding continuously. Compounding continuously just means we should use the formula A equals P times E to the RT. And the interest rate being 5% tells us that we should type R equals 0.05. Now, if I want my account balance to be 100,000, I can plug that in here. I can substitute R equals 0.05 here, and then we can substitute in T equals 1, 2, or 1, 10, 20, 30, 40, and 50 to this formula. And then in each case, we can solve for P, or we can take this equation right now and solve for P. If we take the equation right now and solve for P, we just divide both sides by that e to the RT. The e to the RT reduces. And then remember, if you have 1 divided by x to some power, that's x to the same power but negative. So we can bring this e to the RT up to the numerator if we make that exponent negative. The present value for continuously compounded interest is the amount that we desire to use in the future times e raised to the negative r times t. So for t equals 1 year, I'm saying 1 year in the future, I'd like to have $100,000. According to this formula, we should just substitute 100,000, multiply by e, raised to the negative r, which is 0.05 times t. If t equals 1, we get this $100,000 times e to the negative 0.05. I don't know exactly what that number is, but we can use Desmos to evaluate that. And then if I want to know what that present value should be so that 10 years into the future, I have $100,000, I just have 100,000 times e to the negative 0.05, and then you multiply by that 10 years. And then 20 years is very similar. Everything stays the same. The only thing that changes is that t value that you're substituting. Very, very simple. So we've got a 1 here and a 1 here, a 10 here and a 10 here, a 20 here and a 20 here. And then once we understand how that works, we can just use our table that's generating these numbers on Desmos.com. So let's type a few of these values in to see that we're getting the same numbers that they get in their table. And then once we know that the table is populating correctly, then we can just write down all of the numbers from the table. So our continuously compounded interest formula is necessary for problems 93 and 94. And so we're using this formula. Notice the similarity between that curve and then the other curve. The other curve is for n equals 365. But if we're only compounding interest once per year, the curve would look like that instead. So we can see that they're actually very similar. Even if you're compounding once per year versus 365 times per year. Very, very similar curves. But right now I'm interested in continuous compounding. So we have the present value is going to be the amount that we seek to have t years into the future times e raised to the negative RT. Now, in order to create that table of values, I'll go to that plus sign in the top left corner, click table. We'll use t sub 2 here. And then we want to know what the present value should be to have $100,000 next year, to have $100,000 10 years from now, 20 years from now, 30 years from now, 40 years from now, and 50 years from now. And you can type P sub continuous compounding if you want to. Evaluated at T sub 2. Or if you prefer, you can just type in this formula, evaluated at T sub 2. That will give you the same answer. So you could say A, which is 100,000, times E raised to the negative R times T, but instead of T, we have T sub 2. And now, oops, I wrote T sub 1, I meant T sub 2. Now make sure your R value is what it's supposed to be. So for problem 93, our R value is supposed to be 5%, and that's the correct value of R in decimal form. And so if I'm using my continuous compounding formula for present value, I get these answers. Notice that the second column and the third column are identical to each other. Just in the third column, I just used the formula for that p-value. And then in the second column, I use the name of the function, P sub continuous compounding evaluated at T sub 2. And we see that we get the same value either way. So let's actually type that in. Say, okay, if I didn't have this table auto-populating answers for me, what would I have for P sub 1 or P evaluated at T equals 1? Say, well, what's the present value that I need to deposit? So I have $100,000 next year. What's going to be my A value? So 100,000 times E raised to the negative 0.05, because that's our interest rate, times 1 year. And we get that $95,122.94. So if you want $100,000 next year, you need to deposit $95,000 this year. Say, okay, well, if I had $95,000 this year, maybe I wouldn't be worrying so much about it. Well, yeah, that's a good point. But the idea is hopefully, rather than just waiting, making a deposit and then waiting 1 year, hoping to have $100,000 in the future, maybe you'll wait 10 years or 20 years or 30 years. If you're willing to wait longer, you don't have to deposit nearly as much. So that is for the amount we would have to deposit this year to have $100,000 next year. If you want to have $100,000 10 years from now, instead of evaluating that function at t equals 1, you'll evaluate at 10. So now you only have to deposit $60,000, $60,653. If you deposit that approximately $60,600, now about 10 years from now, you'll have $100,000. So you will have made $40,000 by just waiting 10 years. If you are receiving continuously compounded interest at an interest rate of 5%. Then if we're interested in what happens or how much we have to deposit now to have $100,000 20 years from now, just substitute 20. And it looks like you only have to deposit $36,787.94. And then if you substitute 30, 40, and 50, that looks like the amounts that you need to deposit are 22,000 approximately, 13,500 approximately, and only 8,000. So if you're willing to wait 50 years, you only have to deposit $8,000 now to have $100,000 50 years from now. So you actually make, what, $92,000 by waiting 50 years, depositing that $8,000 now and then just not touching it. So that's how we handle that. We know how to evaluate the formulas ourselves. We know how to type the answers into a calculator and get a decimal approximation of that answer. And since we know how to do that and we know how to create the table, I think that's sufficient for showing that we understand how this formula works. So we're going to do the same thing for 94, which is also dealing with continuous compounded interest, but we've got a different interest rate And then 95 and 96 we're not compounding continuously, but compounding at different rates, not every second or not every moment, but monthly or daily. So let's look at 94 now. Okay, so for 94, we're compounding continuously again. So we take that account balance equals the principal times e to the RT. We solve for p. So we can either divide both sides by e to the RT or multiply both sides by e to the negative RT, same thing. But this time our interest rate is 3%. We're still seeking $100,000 t years from now. So we'll have 100,000 times e raised to the negative 0.03 times t. And then we'll change that value of t to t equals 1, 10, 20, 30, 40, and 50 to populate our table. Since we're still dealing with that continuously compounded interest, we're going to use the same formulas, but I'm going to change my interest rate from 5% to 3%. So I'll make that a 3, I'll make that a 3, and I'll make that a 3. And in order to make sure my table populates correctly, I need to change my slider to r equals 3%. So right now it's r equals 5%, so we're going to write 0.03 for our r value. And then we see that if we evaluate our P formula, where we're using that continuous compounding formula, with r equals 0.03 at 1 year, we get $97,044.55. So if you want $100,000 next year, you need to deposit $97,000 this year. Say, oh goodness, I don't have $97,000. That's okay. Well, what if you're willing to wait 10 years at 3% interest? Well, then you'd have to deposit $74,000 now. I don't have that much. Well, maybe we're willing to wait a little longer. Well, I say, well, what if I want $100,000 20 years from now? Well, I only have to deposit $54,000, $54,881. It's still a lot. Yeah, maybe you should get an account with a better interest rate. That's what I would recommend. But with this particular interest rate of 3%, these are the amounts that you would have to deposit in order to have $100,000 1 year, 10 years, or 20 years from now. We see that the 97,000, the 74,000, and the 54,881 are the values that we have in our table here. So our table is populating correctly. If we want $100,000 in 30 years, we need to deposit $40,656 now. If we want $100,000 in 40 years, we need to deposit about $30,000 now. And if we want $100,000 in 50 years, we need to deposit about $22,000 right now. All right, so that is 94. With 95, rather than compounding continuously, we're going to compound everything monthly. So let's do some calculations on paper for that. Now, since we're talking about compounding monthly rather than continuously, we have to use this formula. We have A equals P times 1 plus that interest rate divided by the number of times we're compounding interest every year, raised to that number of times per year times the number of years. That just gives us the total number of times we're multiplying by this extra factor. We want to solve for P. We can either divide both sides by this or multiply both sides by this exponent or this exponential. But instead of having an NT for our exponent, we'll have a negative NT. So P is A times 1 plus R divided by N raised to the negative NT. Compounded monthly just means we're going to compound interest 12 times per year. And if we have an interest rate of 5%, we're going to write that as 0.05. So if we're seeking $100,000 T years from now, we'll substitute in A equals 100,000. And we're going to add or multiply by 1 plus our interest rate, which is that 5% in decimal form, divided by that number of times per year. So we're taking that 5%, we're dividing it into 12 pieces. That's going to give us some percentage every month. And then we'll raise that to the 12 times T years. So if T is equal to 1 year, we're going to multiply by this number 12 times, once a month. If t is equal to 2 years, we're going to multiply by this extra factor 24 times. If it was 3 years, we multiply by this factor 36 times, and so on and so forth. So this is the formula that we use. Now, for our table, we need to evaluate this at t equals 1 year. So we just raise that expression to the 12. T equals 10 years. If we do that for 12 years, or excuse me, for 10 years, 12 times per year, I'm going to multiply by this extra factor 120 times. We do that for 20 years. I'm going to multiply by that extra factor 20 times 12, so 240 times, and so on. Now, I don't actually know what those numbers are without using my calculator, but we can use Desmos to compute what those values are. And so for problem 95, n is equal to 12, so we can change our slider for n to n equals 12. And our interest rate is 5%, so we can change that to 0.05. Then if that's the case, then these are the principal amounts that we need to, or not principal amounts. This is the present value that we need to deposit so that we have $100,000 T years later. Now, we can evaluate that directly by just plugging in our A value, our R value, and our N value into the formula. Let's look at that interest rate. That was at 5%. We're dividing by 12. So basically, we're adding 0.417%. So 0.417% every month to our account balance. So we're going to take 100% plus this 0.417%, and we'll do that every month for 12 months to get a total of 5% as our annual interest rate. So now if I take 1 plus that, and I multiply that by 100,000, let's get rid of that comma. After the first month, I'm actually going to take that 100 or that 100,000. When I multiply by this, I have, oops, it should be -1. I'll take that 100,000 and then multiply by this, and then raise that to the negative n times t times. So since it's only been 1 month, I'll just have a 1 there, and then t would be 112. I think we just the number of times that the interest has been compounded is 1, so that's going to be fine. So what this says is if I want $100,000 next month, I need to deposit $99,585 right now. Say, well, what if I want $100,000 in 2 months? Well, I need to deposit $99,171.85 right now. What about in 3 months? Say, well, what about in a year? So we're going to have, in a year, we'd have n, which is 12, because we do it 12 times per year, times 1 for 1 year. So we get that $95,132.82. So I need to deposit $95,132.82 at the beginning of the year, so that if we compound interest 12 times per year, at the end of the year, I'll have $100,000. Now, if I want, instead of waiting 1 year, if I'm willing to wait a little bit longer, let's say, I'm willing to wait 10 years, well, then I would need to deposit $60,716 right now. So that means we're multiplying by this interest rate, that 0.417%. And we're adding that to the amount that we have. We're doing that actually 120 times. And if we do that 120 times to this initial amount of $60,716, if we do that 120 times for 10 years, then at the end of that 10-year period, we'll have $100,000 in our account. And then if we want to know what the present value would need to be to have $100,000 in 20 years, you just substitute in t equals 20. So then you'd only have to deposit $36,864.45 right now, so that 20 years in the future, you'd have $100,000. And we see that when we compute these, just by typing in our values to desmos.com and then using the calculator to get us a decimal approximation, we're getting the same values that we have in this table down here. So we have entered our formula correctly, and we can just read the table to find the present value that we should deposit now to have $100,000 in 30 years, 40 years, or 50 years. So if we want $100,000 in 30 years, we need to deposit $22,382.66 right now. If we want to have $100,000 in 40 years, we only need to deposit $13,000, $13,600 approximately right now in order to get that $100,000 in 40 years. If we want $100,000 in 50 years, then we need to deposit $8,251 right now. Now, if you're saying, is it really using the correct formula? You can always type the formula in over here. We have A times that 1 plus R divided by N raised to the negative NT. Oops. Oh, negative N times T sub 1. And we see that we get the same value, whether we use the formula or whether we use the function that we named earlier. And we have the same values, the same entries in the table. All right, so that was for 95. 96, interest is compounded daily and our interest rate is only at 2%. So for compounding interest daily, then N is going to be 365 and our R is 0.02. So it's not a very high percentage rate at all. Then we're going to take our 2%, we'll substitute that here, and we'll divide by 365. After the first year, we've compounded interest 365 times. In order to have $100,000 at the end of the first year for compounding interest daily, we need to deposit $98,000 right now, $98,019.92 right now. Now, if we're willing to wait a little longer rather than waiting a year, if we're willing to wait 10 years, we need to deposit, oh, oops, I need to make sure that base is correct. We're willing to wait 10 years and we're getting that 2% interest rate and we're compounding interest 365 times per year. We need to deposit $81,873 right now and 52 cents. If we're willing to wait 20 years to have $100,000 at a 2% interest rate and it's compounded daily, we need to deposit, oops, that's the wrong number. That should be at 365. We need to deposit $67,032.74 right now. Now, if we go to our table, it doesn't have the right values yet. Or does it? No, it does. So we've changed N to 365. We changed the interest rate to 2%. In decimal form, that's 0.02. So our table is auto-populating with the values that we want. Say, well, what does that mean? We're taking 2% and we're dividing it by 365. So your percentage, I'm going to multiply by 100%. It's not even a 10th or 100th of a percent. It's a half of 100th of a percent. It's 0.005% every day. But if you do that 0.005% interest rate, if you add that much interest every day for an entire year, at the end of the year, you that sort of accumulates to that 2% annual interest rate. So you compound that interest 365 times. And if you do that, then this is the amount in the account that you need to deposit, or this is the amount that you need to deposit now to have $100,000 a year from now. All right. So these are the values. If I want $100,000 a year from now, I need to deposit $98,000 approximately. If I want $100,000 10 years from now, I need to deposit $81,873 approximately. 20 years from now, I need to deposit $67,000. 30 years from now, I need to deposit $54,882 right now. If I'm willing to wait 40 years, I need to deposit $44,933. Then if I'm willing to wait 50 years, I only have to deposit $36,788 right now in order to have that $100,000 in 50 years. So that is how we do that. If you are interested in this, you can play with this little graph and this little, I don't know. I don't know what to call these Desmos graphs, because Desmos calls these a graph, but I think of it as a web page where you have the formulas, you have the sliders, you're able to manipulate the graphs themselves and also manipulate the numbers and then look at tables of values. So I'm not really sure what to call this. But you will have access to this. It'll be linked in the description of this YouTube video. So if you want to, you can change the values of A, R, and N, and change the value of T. Of course, you can change the formulas if you like as well. But these are the formulas that I used for continuous compounded interest, continuously compounded interest, and then compound interest that's compounded n times per year. But again, I would highly recommend that you actually substitute those values into the formula by hand at least a few times to make sure you understand what the calculator is doing. We don't want the calculator to be a black box that comes up with numbers for us and we don't understand what it's doing. As long as you understand what the calculator is doing, I think this is a very appropriate use of technology.